Hi, welcome to week 6. What we're going to look at today, or in this video, is exponential growth and decay. There's another video going to be following this where we talk about exponential functions and logarithmic functions and some of the properties that we use with those functions. But for now, we're going to focus on exponential and growth and decay functions. Exponential growth is where we have a rapid rise. So something like this with a world population starts off fairly linearly and then increases dramatically over the past 400 or so years. This is an exponential curve. Exponential decay, temperature of hot coffee, for example, we just leave it on the bench, it's going to start decaying, and it doesn't actually get all the way to zero, it's going to slowly drift off to room temperature. That's what an exponential decaying function looks like. Now, there's a model that we use to represent exponential growth or decay, and it's this here: f of x equals a, where a is the original value, r is the growth rate or the growth factor, and x is the index. So a is our original value, r is the growth rate. If r is greater than 1, then we have an exponential growth. If r is between 0 and 1, we have exponential decay. Really important that you know this form of it and what a, r, and x represent, and also what scenarios that we're going to have a growth function or a decay function. So what values of r. So we're going to look at a couple of examples now to become familiar with that model. The first one is here. We've got an amount, number of years, and then our amount. This is similar to like a compound growth formula or values. So we're going to draw the graph. Not going to worry about the estimating from the graph. We're going to look at a rule connecting y and a, so the number of years and the amount, and then we're going to work out what that value will be after 20 years. So if we just plot those values, so we start here with 0, and it's a little exponential growth here. It's not, if it was linear, it would just continue straight out this way. Because it's got an upturn, it's an exponential growth. So to look at our rule connecting the number of years and the amount, you're going to use an exponential relationship. So it's going to be in the form of fx equals ar to the power of x. Now remember, a is our original value, so at the beginning we started with $1,000, so that's our a value, and r is our growth rate. That's what we want to find now. So to look at our growth rate, we're going to compare how much that amount is growing every year. So in order to do that, for the first year, we look at what it was at the end of that first year divided by what it was at the start of in year 0, sorry. So we divide those first two values and we get 1.08. So this is our growth rate for the first year, 1.08. So it's increasing by 8%. Growth rate in year 2, 1.08 again the value what it came in the second year divided by what it was in the first year. We do the same for 3 in year 4, and we see we've got a fairly steady growth rate here of 1.08. So we use that and put that into our exponential equation. That should be y equals 1000 brackets 1.08 to the power of x. So number of years. Oh, sorry, I was right. That is the number of years. No, sorry, that is the amount. Let's just erase that. What am I doing? So the amount is going to be 1000 times 1.08 to the power of x, where x is the number of years. So if we graph that function, you can see it connects all the dots up. So what would it be after 20 years? So if our x value is 20, so x was our number of years, the amount's going to be, let's get back out of this, the amount's going to be 100, brackets 1.08 to the power of 20. So after 20 years, our $1,000 will have grown to $4,660. So that's that's what we're talking about when we look at exponential growth. Okay, so the important things are to remember: the initial value is our A, R is our growth rate. If it's exponential growth, it's going to be greater than 1. If it's decaying, it's going to be less than 1, between 0 and 1, and the index is our number of years in this case. We'll look at a second example now. Now we've got, this is running times, and as you can see, after each attempts, the time is decreasing. So we're going to have an exponential decaying function here. So we're going to draw a graph showing her progress. So we're going to plot these points so we show that it is an exponentially decaying function. And then we're going to develop a rule to predict when she'll break the record. So the record is, for 10,000 meters, is 30.25 minutes. These are her trials, these are her attempts and her times. And we're going to come a rule to match up the number of attempts with the time. So if we just plot those, you can see again we've got a slight exponential decaying function, like so. And we want to get that relationship. What is the relationship between the number of trials and the time that she's doing? So again, using the general form, fx equals AR to the power of x. Our A is our original value, so we started, our first trial was 62.85 minutes, so that becomes our A value. Now again, for our growth rate, we're going to see how much it grows each year, or sorry, not each year, that's just some lazy cut and paste. This should be trials. So after the first trial, she's gone from 62.85 to 57.19. So that gives us a growth rate of 0.91. Do the same for the second attempt. We get 0.89. The third attempt, 0.9, and again 0.9. So again, there's a bit of to and froing, but we're going to take the average growth rate, which is 0.9, and use that in our function. So we know that our initial value was 62.85, our growth rate is 0.9, so relating the attempts to the time, this should read time, so time 62.85, 0 times 0.90, and x is our attempts. Excuse me, our attempts. So as we increase our attempts, this time should be getting decreasing. And so if we put that into our equation, our time, when is the time going to be 30.25 seconds? That's when she's going to break the record. For now, we're just going to use some trial and error. In the next video, we're going to look at ways we could solve for that unknown. But for now, it's okay to just use some trial and error. So if we try x equals 6, we put that in there. So again, that's going to be the time. Time equals 62.85 times 0.90 to the power of 6. So after the sixth attempt, her time is going to be down to 33.40. And ignore that, that's not seconds, that's minutes. And on the seventh try, her time should be down to 30.06 minutes. So around about the seventh attempt is when she's going to break that record. Now that's providing it continues to, her times continue to decrease at the same rate. She might plateau earlier, but that's what we're working with. Taking our initial value, finding the growth rate, so it could be exponential growth or decay, but we still call it growth rate, and using that index. So that is all we have for this video. Like I said, it should be fairly familiar type of things you've seen before. Next video is going to introduce some more rules and properties that you can use to find and simplify values using exponentials.